So I'm delighted to welcome you actually on the stage. This is a really interesting development by Hans Schickard. I think this is the MTEK, University of Freiburg branch, if I understand it right. And he's going to be telling us about a process called StarJet technology, which is a direct molten metal printing for printed, flexible, and 3D applications. So welcome on stage.
Yeah, thank you for inviting me. So my name is Zhe Shu. I'm the group leader at Hans Schickard Institute as well as the University of Freiburg. So we are doing applied science research here in Freiburg in Germany. So today I would like to introduce our own development, which is called StarJet technology, which is used for direct molten metal printing for potential printed, flexible, and 3D electronics applications. So I just start straight that what is StarJet technology. So it's very simple configuration. If you look at the right side of the schematic, so basically we build up a reservoir where you can put the metal you want to print inside, for example, tin alloy, aluminum alloy, and with help of the heat around it, when you heat up above the melting point of the metal you want to print. For example, for solder, tin alloy, about 250 degrees. For aluminum, you build higher, more than 660 degrees. Then you will have a liquid phase of metal inside the reservoir. And for printing, we work with actuation, so numeric driven. So that means we have actuation pressure from the top. We give inert gas pressure to the reservoir, which we can push the liquid metal from the reservoir into the reservoir outline, then go to the nozzle chips. And if you look at here, the SEM image of the nozzle chips, which we also manufacture from standard clean room fab manufacturing from silicon chips, also other materials, that it features star-shaped bypass channel with opening in the middle. So that's why we call it StarJet. And with help of this bypass channel and the continuous flow of inert gas, which we call rinse gas pressure, we can generate either jet or single droplets. And also additionally, it provides high directional stability and also prevention of oxidation of the molten metal during the printing. So as we are not working with piezoelectric, that means we can work various different metals which you can melt with configuration, for example, solder, tarmac, or aluminum alloy. And as we are not working with any inks, paste, or particles, so we don't involve any chemicals inside, and we don't need post-treatment. So after printing, it's solidified and conductive. About the operation mode, as I mentioned before, we have two pressure flow, rinse and actuation. So it depends on how you trigger the actuation, either short pulses or continuous pressure. We can operate at either drop on demand, very similar like inkjet, which we can generate very nice single droplets, or you can have continuous flow, which we call jet mode. So you have a continuous liquid flow from the chip orifice. So it's like extrusion. Some first impression. So here you see the StarJet chip holders, and the chip is here, and that we have from this 3 liters. It's the system on top by and heat and single drop. We see that we so show very good printing precision. The same, the jet press, then you have continuous flow. In between, let's say we have jet mode, but then we shoot certain range of pulses, then you can have a short jet and then build up on top of each other. So both shows that we have really good directional stability and also position of print. So if print on the same spot, it keeps at the same places from far away. So enough for the operation mode. We did first application to show, because first of all, you can work with solder. So solder is very typical for